Good evening, everybody, and welcome to the last talk of BSides Las Vegas Proving Ground. Woo! This talk, please inject me x64 code injection by Alon Weinberg. So first, a few announcements. We'd like to thank our sponsors, especially our Inner Circle sponsor, Critical Stack and Valley Mail, and our stellar sponsor, the National Security Agency, Microsoft, and Robinhood. It is their support, along with our sponsors, donors, and volunteers, that make this event possible. These talks are being streamed live, and as a courtesy to our speakers and audience, we ask that you check that your cell phone are set to silent. If you have a question, the audience microphone, so YouTube can hear you. Please raise your hand, and I'll bring it over. Okay, let's get started.
Hey everybody, welcome to Please Inject Me x64 code injection. So first about me, my name is Alon Weinberg. I work at Deep Instinct as a security researcher, researching new attack vectors, malware, versing malware, creating heuristics for many things. Before that, I served at the IDF for 4.5 years. That's pretty much about me. In total, I'm working in this field for 7 years. That's it. Okay, so in this talk, I'm going to talk first a little bit what is code injection. Going to talk about Inject Me, which is a new code injection technique. Before we're going to dive into the flow itself, I'm going to give you some background about some things you need to know before you can execute the code injection. And in the end, there's going to be the flow itself. We're going to talk about the flow. Okay. Okay, so what is code injection? So in general, code injection is inserting code into a remote process and then executing the code in the remote process, in the target process. So through this presentation, I'm going to use the terms injecting process, okay, and target process. So these are the terms I'm going to use in this presentation. So how does it look? We inject code into the target process, then we execute it, and then you get a message box, for example. Okay, so why code injection is important? Code injection can be used for malicious and benign purposes. So let's talk about the malicious purposes. It can be used for stealth. So if you want to, a malware author wants to hide his malware presence from, let's say, a security solution, it can maybe inject the code into the security solution, and they won't run their heuristics against this malware. So it will be able to bypass it. It can be hide from a researcher that is trying to understand what's going on with the malware. It will be harder for him to understand what's going on because it's running in a different process, the actual activity of the malware. And it can be used for stealing information. So let's say phone grabbing in browsers can be used for that. It also can be used for benign users. So security solutions use it to monitor activity of malware. So they can know what it's doing, and if it's malicious, it looks malicious, they can inform you. You can add functionality using code injection to a program, any program. And you can use it to monitor how a program works. So for a researcher, you can see the API calls of a software. Okay, so how it all started. I was researching code injection in general, looking for making some heuristics to detect code injection. And while I was doing it, I thought to myself, maybe I can find my own code injection without using the known methods. So I decided to give it a try, and like it worked. So this code injection it works only in x64. I'm going to abuse x64 calling convention. I'm going to talk about it soon. The main idea about it is we are going to make the target process, okay, read data from the injecting process, and that's how we're going to inject the code. And that's why I'm using the term injectionness, because we're not really injecting code into the target process. We make it read it from us. Okay, so some technical background. So first, you need to know about ReadProcess Memory. ReadProcess Memory is a function in Windows that lets a process read data from another process. Can be the same process, but it lets it read data from a process. It gets 5 parameters, okay? H process is going to be the process we want to read data from. LP base address is going to be where we want to read from, which address we want to read from. LP buffer is going to be where we want to write the data we read. N size is going to be how much we want to read. And LP number of byte read is going to be how much bytes were actually read. Okay? So again, I'm going to abuse ReadProcess Memory and using setThreadContext, which allows us to set a context of a thread. We're going to abuse them to make the target process read data from the injecting process. Okay, so now let's talk about x64 WinAPI calling convention. So in this calling convention, parameters are passed on RCX, RDX, R8, and R9 registers. Okay, so it's possible to pass to a function 4 arguments using registers. In x86, we only do it through the stack. The problem is we can pass only 5 parameters, okay? Only 4 parameters. And after that, if you can see, if you look on the stack, so the first thing on the stack is going to be the return address. There are going to be 4, let's say, 4 fake parameters on the stack, okay? Which are going to be data that is not important. There's not going to be anything interesting there. And after that, there's going to be the 5th parameter, okay? So if we'll see in this example, ReadProcess Memory, going to be R6 is going to be H process, RDX LP base address, R8 LP buffer, R9 N size, and then on the stack, LP number of bytes is going to be on the stack. So that's how it looks like. Okay, so through this presentation, you're going to see this timeline. Okay, so you're going to know where we are exactly at. We'll first talk about setting up ReadProcess Memory. Then I'll show you the first problem I encountered while doing this, which is an access violation. We'll then create an infinitely running thread to solve another problem, and in the end, we're going to execute the code injection. Okay, so setting up ReadProcess Memory. ReadProcess Memory, as I showed earlier, gets 5 arguments, okay? And as stated, we can only pass 4 arguments, okay, on the registers. Lucky for us, the 5th parameter can be null in ReadProcess Memory, and then it's ignored. So we can make it null and it will be good. More lucky for us, if you use virtual alloc X, it allows us to allocate memory in the target process, and it's going to be all zeroed out. So the 5th parameter is going to be ignored using that. So that's how we are going to create the 5th parameter. We're going to create a dummy stack that is going to be a fake stack with all zeroed out, and that's going to be the 5th parameter. Okay, so now we'll start. Let's say we're now starting to set up a ReadProcess Memory for abuse in the remote process. Okay, so first thing, we need H process. H process, the handle of the process we want to read from. Okay, so the target process wants to read from the injecting process. It needs a handle to the injecting process. So we take the injecting process and we duplicate its own handle into the target process. And that's how we're going to give it later. We're going to pass it as the parameter of H process. After that, we are going to allocate memory for our shellcode. And if we look at all the things, so as we said, we have the H process. We're going to the handle of the process. We know where the shellcode resides because it's in the injecting process. The buffer we want to copy to is going to be the memory we allocated. The size is going to be the size of the shellcode. and LP number of bytes is going to be null because we're going to have a dummy stack. So that looks good so far, but okay, so let's say we look at the stack, and the stack is going to look like this because it's all zeroed out. So we call read process memory. The memory is read to the buffer. We return to the address on the stack, and access violation. It's trying to jump back to 0. Can't happen. So we're getting an access violation, which is bad for us. The process is going to crash, and we can then execute our code. But if we use the function, let's say we'll put on as the return address the function RTL exit user thread, okay? When we'll run read process memory, we'll call read process memory. It will be read. Return address will be on the stack. It will going to be RTL exit user thread, which is going to exit the thread safely, and then we won't have a problem. The program won't crash. Amazing. Okay, so now we know that we need RTL exit user thread on the stack. So to do so, we will need later on to find somehow to put it there, and I'm going to explain how we do it. So first, let's talk about kernel 32 and NTDLL. For those who don't know, these are DLLs that exist in Windows. When they are loaded in the processes, they are loaded to the same address, okay? And their IIT, which is import address table, going to be also, because it's relative to the base address, it's going to be the same address in every process. So let's say we find the address of RTL exit user thread in NTDLL, okay, or kernel 32. We can copy it. We're going to copy it in the target process by just finding the location, and then we find it. It's going to be at the same location in the target process, and we're then going to copy it. I'll show you how we do it. We will copy it there. So, okay. So how do we copy? There's a function known as ntqapc thread. This function allows you to run code, okay, in a remote thread. So you can run a function in a remote thread. We are going to use RTL copy memory, which allows us to just copy memory. And as I said, because we found earlier in kernel 32, we found, okay, sorry. In kernel 32, I forgot to say that. I'll go back a little bit back. Kernel 32 is importing the function RTL exit user thread, okay? And because it's importing RTL exit user thread, the address is going to be in kernel 32. It's going to be also at the same place in the target process, okay? So that's how we're going to copy that into the stack. Okay, so how do we copy it? We're going to use the function RTL copy memory. With this function, you pass to this function destination, source, and length. It allows you to copy memory in the place that is executing this function. And we can use ntqapc, which gets the parameters of a thread we want to execute in code. We're going to execute in that thread RTL copy memory. And ntqapc also allows you to pass 3 parameters to that function, which is good for us, exactly what we need. So we're going to execute using that function in the target process, RTL copy memory, with the destination is going to be the stack return address. The source is going to be the address we found of RTL exit user thread, and the length is going to be 8 bytes, which is the pointer size. Okay, so now a little side note. Because we know now how to copy data in a remote process, in the target process, we can use that to recreate a shellcode. So you can just go byte by byte in the shellcode, find those bytes in, let's say, NTDLL version of the injecting process. It's going to be on the same place. It's going to be the same at the target process. So we can just recreate the shellcode. But then you need to call this function as many bytes as, like, if there's 100 bytes, it's going to call it 100 times. So it depends on the size of the shellcode. It might take a lot of time. OK, so now let's finalize the code injection. OK, so what first I thought I should do is maybe I just change RIP, OK, the instruction pointer, to point to read process memory. I'm going to set RCX, RDX, I'm going to set those registers, and then just make the remote process, the target process, execute those, execute read process memory. But the truth, what happens if you do so, you get status invalid parameter. So what we need now, we need to let a thread to initialize before we can manipulate it, before we can change RIP or do something with it. But if we'll start a thread and it we'll just execute it and won't create it suspended and let it initialize, it's going to terminate right away. So we want to create an infinitely running thread. Will let us time to initialize it, and then we have time to manipulate it because it's just keep running, it's not stopping, it's not terminating. OK, so now if you look here, probably you can't see it, but when you start a new thread, this thread is going to start at RTL user thread start. This function first calls another function, and then there's going to be jump RAX. Okay? In the middle, you probably haven't noticed yet, jump RBX is never touched. So I'm going to use RBX to create an infinitely running thread. Okay, so what I'm going to do? First, I'm going to allocate memory for jump RBX. Okay, this memory is going to be read, write, execute. So we can write there and execute there. We will look for jump RPX opcode, which is the size of 2. We're going to look for it in our version of NDDLL. Then, using the method I described earlier to copy data, I'm going to copy the opcode into the allocated data, the allocated memory. We will create a suspended thread, okay? Then we'll set RBX, which is not touched, to the jump RBX, okay? Then we'll resume the thread, and what's going to happen, just going to run through the functions I showed you, going to get to jump RBX. RBX is pointing to the same location as jump RBX, and just going to jump over and over again to the same spot, and then it's just going to run infinitely. Great. Okay, so now we want to execute and finish things up. So what we're going to do, we'll suspend the thread, be sure that RIP is now pointing to the jump RBX, so we know that things were initialized already. And then we'll start setting the thread context, okay? So we're going to set RCX. I'm going to talk about how we set them. RCX is going to be the duplicated enter, okay? RDX is going to be the location of the shellcode in the injecting process, okay? R8 is going to be the allocated buffer we have. R9 is going to be the size of the shellcode, okay? RSP is going to be the dummy stack, okay? And then we set RBX to read process memory because we are now in jump RBX, so when we change it RBX to read process memory, just going to jump to read process memory. Then we use wait for single object just to see that when we resume the thread, we wait for it to run, so we do wait for single object. We see that the thread was terminated. The data was copied into the target process, and then we can execute it using one of the many known methods of executing code. Let's say create remote thread, and then we can execute the shell code. Okay, now time for demo. Great. Okay, so in this demo, I'm going to show, well, it's not in a good quality, but I'm going to show you that I'm going to open a notepad, okay? Then I'm going to inject code into this notepad, and you're going to see a message box that shows you the command line of the message box. So that's what you're going to see. So I open up the notepad. Now I'm executing the code. So first we duplicate the handle. Now we allocate memory for the shellcode. Then we allocate the stack. We copy RTL exit user thread to the stack. Now we allocate memory for jump RBX. It was copied. We find read process memory. Then we make the entry point of jump RBX. We set the thread context. We execute read process memory. We execute the shellcode. And as you can see, now there's a message box showing the command line of Notepad. So thank you guys for having me. The research paper is not available yet. It will be available in a few days. You're more than welcome to read it. Thank you very much. Are there any questions?
Questions? Just raise your hand. No questions?
Okay, great.
Okay, cool, great.
Okay, thank you very much, guys. Thank you very much.
Good.